did. Let's quiet down. So the roots of polynomials are also called zeros, x-intercepts, and solution. So if I ask you for any of those things, I'm just asking you to tell me what's on the x-axis, okay? All right, so here's my polynomial. This is the one I'm focusing on. I want to know how many turning points. How many do I have? 2. Good. All right, and then the degree is 1 more than the turning point. So what's the degree? 3. Now we do have to start knowing these words. For now, I have them up here, okay? But if the degree is 3, then we know it's cubic. But you need to start remembering these words. Now, the arrows aren't there, but you guys know that I meant to put arrows there. And so for a domain, you put negative infinity to infinity, right? And remember that every polynomial will go all the way left and all the way right, so that's always going to be your domain for a polynomial function. The range sometimes is the same and sometimes it's not. It depends, right? If the arrows go the same way, then you might have a minimum point or a maximum point. But when the arrows go opposite directions, then you still have negative infinity all the way to positive infinity. Does it matter what order you put your infinities? Yes. You always have to put the smallest number first and then the largest, so that would be negative infinity and then positive infinity. It's never going to be switched. Okay, increasing and decreasing intervals, do we look at the x-axis or the y-axis? X-axis. So remember to use the x-axis. And last class, I told you to connect your turning points to the x-axis to help you do that. And also add your negative infinity on the left and your positive infinity on the right. So then the first one is decreasing negative infinity to -1. And then increasing from -1 to +1. And then finally decreasing from 1 to infinity. What questions do you have? If you got a number wrong, it's possible you were looking at the y-axis instead of the x-axis. Okay. The y-intercept is where you cross the y-axis. You want to write this one as a point. So the x is 0. Everywhere you have a y-intercept, the x will be 0, and then the y is 1. So notice that the point looks just like an interval, but they're different. The point is like one point on the graph, and the interval is like a whole set of points. Okay. So it says leading coefficient, not leading term. So we don't want to include the x's. We just want the number in front of the term with the biggest exponent. So I find my biggest exponent, and then I find my leading coefficient. And then end behavior. So we always are going to have as x goes to infinity. And we're always going to have as x goes to negative infinity. Okay, so we're always going to talk about the right side and the left side. And then what changes is what the y does. So on the right side, the y is going to what? Negative infinity. Morning, Anna. And then on the left side, x is going to positive infinity. Good morning, Drew. Thank you. Okay. What questions do you guys have before we start moving on to the new stuff? We're good? Oh wait, I didn't finish it, did I? We have to do this part down here. State the zeros or roots from the graph. So that means like actually what points are they or what number are they? If they asked for the x-intercept, then you would write it as a point. So these will just be numbers. And just crosses one time at 2. How many roots are there? So I'll vote for 3. Remember, it's the same as the degree. Move that up. Same as the degree. So degree is 3, which means 3 roots. Okay, so we had only 1 real root, which means we have how many non-real roots? 2 fake roots. And it says, remember that complex roots always come in pairs. So you could have 2 imaginary roots, 4 imaginary roots, 6 imaginary roots, but you'll never have 5 imaginary roots because they always come in pairs. Questions? Yes.
For like state the zeros / roots from the graph,
Mhm.
we don't write that as a point.
I probably wouldn't take off if you wrote it as a point, but the one that has to be a point is the x-intercept. If I say x-intercept, I need a point.
Yeah.
The rest of them, you can just write them as the number. All right, so we are going to start talking about these graphs down here, and notice that we're not given a graph. Today, we're going to learn how to graph these without a calculator, and it's really not that hard. It's just putting some pieces together, okay? All right, so before we graph it, we're going to fill in the bottom part. I know some of you didn't get this top part. It's actually just review from last class, so you could do it on your own, or you could just wait and get that from the key. Let's go down here. Okay, looking at this, we have the same equation in standard form and in factored form. Standard form is going to be helpful for some of these things, and then factored form is going to help us actually finish up the stuff we need to graph it. What is the degree of the first function? It's 3, good. So my degree is 3, which means my total roots is 3. Roots from the graph. So I don't know yet what the roots are, but I can find them because remember, everywhere on the x-axis, your y is 0. So I can set my factors equal to 0 and find out what my x-intercepts are. So I can write x equals 0. Good morning, Nor. X plus 2 equals 0. And x minus 1 equals 0. Like, why did I put it on the side here? Oh, because I was going to solve this one. X equals 0 is already solved. But if I solve this one by subtracting 2 on both sides, I'll get x equals negative 2. And then I can solve this one by adding 1 on both sides, and I get x equals 1. So these are my roots. I'll write them in order, but it doesn't actually matter. So you can put those on the graph. These are my x-intercepts, 0, 1, and negative 2. All right, to find the y-intercept, you make what equal 0? You guys know, it's the x, thank you. So it doesn't matter which equation you use, but I'm going to use this one. So it would be 0 to the third plus 0 squared minus 0, which is just 0. So it'll be the point 0, 0. And I already have that point marked. Okay, we don't know the end behavior yet. That's something we're about to learn. But we do know the leading coefficient. The leading coefficient, go ahead, hon.
Why would you not add the 2 from the original equation?
Oh, I can. So it would be like 2 times 0, but that's still going to give me 0. All right, the leading coefficient is in front of the term with the biggest exponent, and so that is 1.
Wait, how did you have it written before you added the original stuff?
I had 0 cubed plus 0 squared minus 0. And then Marin reminded me that there's a 2 here, but 2 times 0 is still going to give me 0. Okay, here's what we're going to learn about end behavior. The leading coefficient the leading term altogether tells you the end behavior of the graph. Remember that the end behavior happens as x gets really, really, really big, right? Like infinity. All right, so let's say, like, for example, x is like 1 billion, okay? 1 billion cubed, here's 1 billion cubed, is much more important than 1 billion squared, okay? 1 billion cubed is going to be gigantic. 1 billion squared is pretty big, but not as big as 1 billion cubed. So the leading term, when you do end behavior, the leading term is the one that really matters. The rest of it is just like extra, okay? This is the term that's going to tell you what happens as x gets super, super big. Also as x gets super, super small, but it's easier to focus on one thing at a time. So as x gets super, super big, if this number in front is positive, then the y value is going to get really, really, really big, really positive. If the y value is negative, then, if the coefficient is negative, then your y value is going to get really, really, really negative, okay? So if this number is positive, the right side will go up. If this number is negative, the right side will go down. I want to show you that on these functions that you already know. Okay? The parent function y equals 1x, the right side goes up. Parent function y equals 1x squared, the right side goes up. Okay? Then also your exponent is going to tell you what happens on the other side. If your exponent is odd, then as x goes to negative infinity, the y is going to go down. So when you have an odd exponent, your two ends are opposites. When you have an even exponent, then your two ends are going to be the same. So both up or both down. Okay? So these examples can help you figure out like any lead term. If I gave you the lead term, negative 5x to the 7, the negative 5 would tell you that the right side goes which way? Down, right? Negative 5 tells you the right side goes down. And then the 7 tells you that they don't match. The ends don't match. So the left side would go which way? Up. Good. Are you eating? Yeah. Okay. All right. So we're going to use this now so that we can sketch our graph. You always put in your x-intercepts, you put in your y-intercepts, and then you sketch your end behavior, and then you're pretty much ready to go. Okay? So my end behavior depends on the 1. That tells me that the right side goes up. I am going to actually write the whole statement. I just want to draw a sketch first. The right side's going to go up. And then the exponent is odd, which means the ends don't match. So the left side's going to go down. So now let me write the statement for that. As x goes to infinity, that's going to be the right side here. The y goes to infinity. As x goes to negative infinity, the y is going to go down. The y goes to negative infinity. So we actually have everything we need to sketch the graph now. Obviously, we're not going to get the heights correct, and that's okay. It's just a sketch. We have the important features in it. You see that? Make your end behavior match, and then go through your points. It says make a connection between the factors and the real roots, and we just set those factors equal to 0 to find the real roots. Okay. In number 2, I am going to show you one thing that happens different about the graph. So I want you to do as much of this as you can. As much of this here as you can. But then I'm going to help you with sketching the graph because there is something new and different in this one. Okay? So take a moment to do this one. You're going to... Okay. Degree is your biggest exponent, so you should have put 4. 4 is your biggest exponent, which means also that there are 4 total roots. The roots from the graph, you guys took these and you set them equal to 0. So x plus 1 equals 0 gives me x equals negative 1. X minus 1 equals 0 gives me x equals 1. And then x minus 3 equals 0 gives me x equals 3. Do you guys have any questions on those? Okay. So the roots were negative 1, positive 1, and 3. So you should graph those, negative 1, positive 1, and 3. For the y-intercept, you had to make the x's 0. So this is going to be 0. That's 4 times 0, which is still 0. Negative 2 times 0, still 0. Negative 4 times 0, still 0. But then plus 3. So what's your final answer? What's your y-intercept, guys? 3. Your y-intercept's 3. Because it was 0 plus 0 minus 0 minus 0 plus 3.
So we don't have to worry about the exponents when we do that?
Yeah, because 0 to the third is still 0, right? 0 to the second is still 0. Yeah. All right, so then my y-intercept is the point 0, 3, and I need to graph that one up here. All right, I did see a lot of you on your graphs, you had marked the origin. The origin is not marked on this graph. Okay, let's do end behavior. So the leading coefficient is negative 1, which means the right side goes which way? There?
Yeah.
Okay. All right, so the leading coefficient was negative 1, which means the right side goes down. And I'm just doing my sketch first. And it was even, which means that the ends match or don't match? They match. So they're both down. So now let's write our statements. As x goes to infinity and as x goes to negative infinity. Okay, since they're both down, both y's are going to what? Negative infinity, good. New. All right, if you think this through, some of you have sketched it in already to make it look like this, but actually it's a little bit different. And it's because of the root that's squared right here, okay? The root that's squared creates a bounce off the x-axis at x equals 1. When one of your factors is squared, the behavior of the graph is that it bounces off the x-axis. So I'm going to see if I can make this make sense. So it's going to go here, it's going to bounce, and then it's going to go here. Now, just because this is my y-intercept does not actually mean it's a maximum point. It could actually have a maximum to the left or to the right of it, but it does go through that point.
So, would it just be like bounces it makes it go up instead of down?
So instead of going through the x-axis, it hits that point and then bounces back up again. And we're going to talk more about that on the back, but I want to make sure you got that shape in right. So, it says number 2 has no non-real roots, right? But we only see 3 roots, and we know there's how many roots altogether? 4. So why would it have no non-real roots? So it is related to this one it doesn't go through, because do you guys remember that this factor is squared? Go ahead. Oh, I thought you were raising your hand. This factor here is squared. Right, so that means that x equals 1 is a root 2 times. So the roots are 1 and 1, negative 1, and 3. Okay, so a multiple root can count more than one time. You don't list it twice because that's dumb, to say, oh, the roots are negative 1, 1, 1, and 3. But because of the double root, we really do have 4 real roots. And remember, a factor could be raised to any exponent. Factor could be cubed or to the fourth power, so it could be a triple root, it could be a quadruple root, like a root could show up multiple times. All right, what questions do you have before we go to the back? I'm going to take a 60-second processing break. It is not an electronics break. All right, so we're going to talk about the multiplicity of roots. And remember in our last graph, we had that graph where we had a double root and it made that bounce in the graph, okay? So when you have a multiplicity of 1, which is usually what you have, right? This factor will create a 0. And you add 2 to both sides and you get x equals 2. And so you'll have a 0 at 2. And your graph will just pass straight through. Okay? Pass through the 0. I'll say root. And then what we discovered in the last graph was that when your factor is squared, then you're going to bounce off the x-axis at the root. So you still have a 0 at 2, but the behavior is that we bounce off the x-axis at the root. All right, think about what a multiplicity of 3 does. Think about your cubic graph, right? Y equals x cubed. Remember that one? It kind of goes up towards the 0, the origin, and then it like has that little wiggle, and then it goes back up again. That's the behavior when you have a 0 that is to the 3rd power. So if we set this equal to 0, we still get x equals 2, but it's going to pass through with a little wiggle. All right, so you see how it doesn't go straight through? It actually changes its concavity right there. It's like a point of inflection. All right, and then this one, the last one, actually it's not the whole factor that's squared. It's just that x that's squared. So if I set this last one equal to 0, look what happens. Subtract the 2. X squared equals negative 2. What kind of roots am I going to get? X equals plus or minus. Remember how I said imaginary roots come in pairs? That's why, because of the plus or minus. I root 2. So you're getting imaginary roots. Do imaginary roots cross the x-axis? No, good. All right. So, might be something like that. Does not cross the x-axis.
Can you go up a little bit so I can see the graph?
Yeah, let me just do my high-tech zoom.
Can you put it like anywhere?
Oh, yeah, I just sketched it. I didn't actually try to put the points in the right spot. It's actually over here, if you want to have it right. Because it should have been just shifted up too. But that's okay. All right, I'm going to do 4 with you, so then you guys can go back and do 3. Notice in 4, it's not factored, so we're going to factor it. I'm telling you, factoring comes back over and over again. This year, next year, for the rest of your mathematical career. All right, so we're focusing in on 4. All right. They don't have any coefficients that we can divide by, but we could divide them by what? By x. And in this case, they actually can all be divided by x squared. Because remember, when you divide, you subtract exponents. So we can factor x squared out. So I'm going to put the x squared on the outside, and then I have x squared minus 2x minus 8. Okay, and I know that it's really hard to see that. Let me fix it for you. And then I need two numbers that multiply to negative 8 and add to negative 2. And if you think of them, tell your neighbor.
Wait, what do you need?
Multiply to negative 8, add to negative 2. Okay, so your numbers are 2 and what? 2 and negative 4, thank you. So 2 times negative 4 gives you negative 8. 2 plus negative 4 gives you negative 2. Whew, factoring. It's all coming back. Okay, so each of those factors gives you a 0. X plus 2 gives you what 0? Negative 2. X minus 4 gives you positive 4. And x squared equals 0. X squared equals 0 gives you x equals 0. Still 0. Okay, so if I were graphing this function on the x-axis, I would mark negative 2, positive 4, and 0. But I need to know, does the graph go through those points, or does it bounce, or does it go through with a wiggle? So the first one, negative 2, that factor is to the first power, so its multiplicity is 1. The 4, that factor is to the first power, so its multiplicity is 1. And then the 0 is to the second power, so its multiplicity is 2.
Wait, how did you get 0 then?
I set the x squared equal to 0, which gave me x equals 0. All right, so the effect of a multiplicity of 1 is just pass through. And then what is the effect when the multiplicity is 2? Bounce. Good. Okay. Now, this is all factored out, but I can see the degree from the original is 4. But what if I didn't have the original and I just had the factors? How could I find out that the degree is 4 from the factors? That one is a 2, right? This one is a 1. And then this one is a 1. So remember, when you multiply, you add exponents. So I could just add my exponents, 2 plus 1 plus 1, and I could also get a degree of 4. Okay? All right, so this one over here is factored for you. I want you to find the zeros, multiplicity, and effect. Most of you are getting 2 of the zeros right, but I see some mistakes on one of the zeros. So let's just check your work, okay? X plus 7 equals 0 gave you a 0 of negative 7. Did you get that? And x minus 4 equals 0 gave you a 0 of 4. Did you get that?
Yes.
Okay. The middle one, 2x plus 1, it's a two-step process, so it might be helpful to actually write it down.
Wait, do we have to put it in that order?
No, you don't. You can put it in any order, it's just a list. All right, so 2x plus 1 equals 0. You're going to subtract the 1. And then divide the 2. And we get x equals negative 1/2.
Why
So we have a 0 at -1/2 or -0.5. Okay, so then for the multiplicity, this is 1 and this is 1, and then that one is 3.
How do you get the multiplicity?
So you look at the exponent on the factor. So this is 1, 1, and then 3. Okay, the degree was your biggest exponent, so it was 5. So we're going to do these two. So this one says, is the graph going up or down on the right side? We don't have to graph it because you know what's going to happen. The leading coefficient is 5, and that tells you that the right side goes which way? Up. Because the leading coefficient is positive. All right, let's look at this one. We're going to look at your leading. Oh, actually, for this one, it says end behavior, same direction or different. So then we look at the exponent. The exponent is odd, which means that the ends are which? They're different. They're opposite. Okay, you guys do these two. All right, this time your lead coefficient is negative, which means that your graph is going down. Did you get it right? Good. And in this one, your exponent is even, which means that the two ends should match. They're the same because it's even, okay? Odd, even, positive, negative. All right. What questions do you have?